In today's video, we are peeling back the layers and diving deep into the essentials of system design requirements. Let's understand the pillars of system design and what it really takes to create a robust and resilient application. Now, before we jump into the technicalities, let's talk about what actually makes a good design. When we talk about good design in system architecture, we are really focusing on a few key principles. Scalability, which is our system growth with its user base. Maintainability, which is ensuring future developers can understand and improve our system. And efficiency, which is making the best use of our resources. But good design also means planning for failure and building a system that not only performs well when everything is running smoothly, but also maintains its composure when things go wrong. At the heart of system design are three key elements: moving data, storing data, and transforming data. Moving data is about ensuring that data can flow seamlessly from one part of our system to another. Whether it's user requests seeding our servers or data transfers between databases, we need to optimize for speed and security. Storing data isn't just about choosing between SQL or NoSQL databases, it's about understanding access patterns, indexing strategies, and backup solutions. We need to ensure that our data is not only stored securely, but is also readily available when needed. And data transformation is about taking raw data and turning it into meaningful information, whether it's aggregating log files for analysis or converting user input into a different format. Now let's take a moment to understand the crucial concept in system design, the CAP theorem, also known as Brewer's theorem, named after computer scientist Eric Brewer. This theorem is a set of principles that guide us in making informed trade-offs between three key components of a distributed system: consistency, availability, and partition tolerance. Consistency ensures that all nodes in the distributed system have the same data at the same time. If you make a change to one node, that change should also be reflected across all nodes. Think of it like updating a Google Doc. If one person makes an edit, everyone else sees that edit immediately. Availability means that the system is always operational and responsive to requests, regardless of what might be happening behind the scenes. Like a reliable online store, no matter when you visit, it's always open and ready to take your order. And partition tolerance refers to the system's ability to continue functioning even when a network partition occurs. Meaning if there is a disruption in communication between nodes, the system still works. It's like having a group chat where even if one person loses connection, the rest of the group can continue chatting. And according to CAP theorem, a distributed system can only achieve two out of these three properties at the same time. If you prioritize consistency and partition tolerance, you might have to compromise on availability and vice versa. For example, a banking system needs to be consistent and partition tolerant to ensure financial accuracy, even if it means some transactions take longer to process, temporarily compromising availability. So every design decision comes with trade-offs. For example, a system optimized for read operations might perform poorly on write operations. Or in order to gain performance, we might have to sacrifice a bit of complexity. So it's not about finding the perfect solution, it's about finding the best solution for our specific use case. And that means making informed decisions about where we can afford to compromise. So one important measurement of system is availability. This is the measure of system's operational performance and reliability. When we talk about availability, we are essentially asking, is our system up and running when our users need it? This is often measured in terms of percentage, aiming for that golden 5 nines availability. Let's say we are running a critical service with 99.9 availability. That allows for around 8.76 hours of downtime per year. But if we add 2 nines to it, we are talking just about 5 minutes of downtime per year. And that's a massive difference, especially for services where every second counts. We often measure it in terms of uptime and downtime, and here is where service level objectives and service level agreements come into play. SLOs are like setting goals for our system's performance and availability. For example, we might set an SLO stating that our web service should respond to requests within 300 milliseconds and 99.9% of the time. SLAs, on the other hand, are like formal contracts with our users or customers. They define the minimum level of service we are committing to provide. So if our SLA guarantees 99.99 availability and we drop below that, we might have to provide refunds or other compensations to our customers. Building resilience into our system means expecting the unexpected. This could mean implementing redundant systems, ensuring there is always a backup ready to take over in case of failure. Or it could mean designing our system to degrade gracefully, so even if certain features are unavailable, the core functionality remains intact. To measure this aspect, we used reliability, fault tolerance, and redundancy. Reliability means ensuring that our system works correctly and consistently. Fault tolerance is about preparing for when things go wrong. How does our system handle unexpected failures or attacks? And redundancy is about having backups, ensuring that if one part of our system fails, there is another ready to take its place. We also need to measure the speed of our system, and for that we have throughput and latency. Throughput measures how much data our system can handle over a certain period of time. We have server throughput, which is measured in requests per second. This metric provides an indication of how many client requests a server can handle in a given time frame. A higher RPS value typically indicates better performance and the ability to handle more concurrent users. We have database throughput, which is measured in queries per second. This quantifies the number of queries a database can process in a second. Like server throughput, a higher QPS value usually signifies better performance. And we also have data throughput, which is measured in bytes per second. This reflects the amount of data transferred over a network or processed by a system in a given period of time. On the other hand, latency measures how long it takes to handle a single request. It's the time it takes for a request to get a response. And optimizing for one can often lead to sacrifices in the other. For example, batching operations can increase throughput but might also increase latency. And designing a system poorly can lead to a lot of issues down the line, from performance bottlenecks to security vulnerabilities. And unlike code which can be refactored easily, redesigning a system can be a monumental task. That's why it's crucial to invest time and resources into getting the design right from the start and laying a solid foundation that can support the weight of future features and user growth. And that's a wrap. Check out this deep dive into system design concepts to elevate your design skills further. See you in the next video.